Hi everyone. In this video, we will explore an updated definition of the limit that will work in a more general case than the limit definition we saw previously. So recall that in earlier lectures, we looked at this epsilon delta definition of a limit. This definition is due to Weierstrass. And the idea is let f be a function which is defined on some open interval which contains a point A, except the function may possibly not be defined at a point A itself. Then we say the limit as x approaches a of f of x is equal to L if and only if for every epsilon greater than 0, there is a delta greater than 0, such that for every x in the interval I, if the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L will be less than epsilon. So first, a few things to note. What we want to pay particular attention to today is the restrictions that we place on f and on the point A in order for us even to make sense of what the limit ought to be or whether the limit even exists. So in this particular case, right, recall that we're requiring f to be defined on some open interval I containing A. So, right, the general sort of picture we would draw here, right, I have a function and on some interval, it could be quite a small interval, right? My function has to be defined at every point in this interval except possibly at A. So, right, I could have an open circle here at A. And now outside of here, right, so my function could look like this, and then it could be some discrete points, and over here, there could be right, all sorts of things can happen here. But I at least require that if I want to talk about the limit at x is equal to a, my function has to be defined on some open interval which contains a except possibly at a itself. Now, if you think back to when we first started this sort of rerun through things, we first spent a lot of time defining properties of sets. And if we look at this definition, right, I want to look at a set which is an open interval containing A, except possibly A itself. That ought to look sort of similar to something we were just talking about, and that is actually the concept of a deleted neighborhood. So we could actually rephrase this first bit now to say instead, let f uh, be defined on the deleted neighborhood of radius r around A for some r greater than 0, right? So really this condition is saying that your function needs to be defined on some deleted neighborhood of the set, of the point A. Now, these are actually not exactly the same because this just says an open interval I containing A. So for example, it would be possible that this open interval could be like asymmetric, right? So your open interval could be something like this. But if that is the case, then certainly, right, I could create a symmetric interval around there and use that to then build my deleted neighborhood. Um, so these end up being equivalent in forming the definition, even though maybe in the particulars there's a slightly nuanced difference. So this definition requires that to even make sense of starting to talk about the limit, I have a function which is defined on a deleted neighborhood of a point of the point in question. Now, you may see sort of no problem with that. But what I'd like to do is start by looking at an example to see maybe why we might want to relax this definition and how we might start to go about doing that. So I want to start by looking at a particular example. So I want to consider the function f of x, or sorry, the function f, which maps from a set D, the domain, into R. It's going to be defined by the equation f of x is equal to x. So sort of before we even go on and look at the rest of this, I think intuitively you feel like this should be easy, right? This is the identity function. right? Um, but what makes this a little difficult here is our set D, our domain, is not a typical set, right? So I want to take the set D to be the set of all values 1 over n, where n is a natural number. Okay? So we actually looked at this set in an earlier video. In fact, one of the things we showed in that video, maybe a bit of foreshadowing, is that 0 is not in the set D, right? 0 is not of the form 1 over n for some natural number, but 0 is an accumulation point of this set D. And finally, we also sort of briefly mentioned that every other point in this set is an isolated point. So, well, sorry, 0 is not in the set. So every point of this set is an isolated point. There is an accumulation point 0, but 0 is not actually in that set. So all points in D are isolated. Okay, so just briefly recalling some facts about those. A good chance to go back and review these in the earlier video if you've sort of maybe forgotten about some of these things. So that's our domain. Let's think about how does that translate into a function. Well, let's actually look at a graph of this function. Okay, so right, it's just the identity function. So for every x value in my domain, right, I'm just going to use the same y value, and I'm going to just get all of these points that lie along this. You can maybe sort of see faintly in the background here, I have a little dashed line representing the line y is equal to x. And so for every value that's in my domain, we get a point lying on that line. So we get the point 1, 1, we get the point 1 half, 1 half, we get the point 1/3, 1/3, 1/4, 1/4, 1/5, 1/5, so on and so on and so on and so on and so on. Now, if we sort of look at this function, if I asked you, what's the limit as x approaches 1, I think you might immediately sort of say, well, there's no way we can make sense of that. Certainly under our old definition, we can't, right? There is no interval around 1. There's no deleted neighborhood around 1 such that this function is defined on that entire deleted neighborhood, right? It's defined at 1, and then because it's isolated, there's nothing nearby 1 where my function is defined. Same thing at 1 half, same thing at 1/3, same thing at 1/4. Now, as we get down here, you might start to scratch your head a bit, and in part this is due to the limitations of the plot. This starts to look like a continuum, even though it's really a bunch of discrete, isolated points. Okay, so this continues to be true, even though maybe this picture is slightly deceiving. So we maybe feel like, and certainly under our old definition, the limit is not going to exist at any of these points. Okay, but I sort of feel like if I track these points, like I should be able to say something about what's going on as I look at the sequence of these points, right? And which makes me start to wonder, could I say something about the limit at 0? Now, under our old definition, we could not. Okay, so if I were to think about 0 here, right, and maybe sort of imagine I come over here and I'm going to sort of, zoom in on 0. Okay, so near 0, what am I going to see? So let's say here's 0. Well, the first problem you have, so there's no point. Well, I'm trying to say there's no point and then drew a point. There's no point of my function at 0. Okay, but you have these points that are approaching it in some sense, right? And as you get further out, it becomes clearer that they're all isolated, but as you get further away, the gaps grow larger, so it's a little clearer that they're even more isolated. Now, any interval I draw around 0, so no matter how small this interval is, I have two problems. One is any interval I draw around 0, if it extends to the left over here, right, which it has to because the interval I has to contain A, has to contain 0. If it extends over here, my function isn't defined over here. So already that fails. But also, even if maybe I allowed myself to sort of exclude that half of it and just looked at this half, sort of thinking more of a one-sided limit situation, um, if I were to look over here, still, no matter how close I move this point over to 0, there's still going to be gaps between these points. There's still going to be places where my function is not defined. So again, even though it really feels like maybe I should be able to say something about the limit at 0, under our old definition, that simply won't work. But from observing these properties about our domain and about 0 before, right, we notice 0 is not just, it's not in my set, but it is a special point related to this set, which is that 0 is an accumulation point of the domain. So what we want to do is we want to look and ask ourselves, would it be possible to extend this definition to accumulation points of the domain? And if so, what other changes might that necessitate in our definition? So now we want to look at a new definition and compare and contrast it to our old definition. So our new definition will say, let f be a function from D. Here, D is just a general domain. It's not the specific domain I previously defined. So let f be a function from D into R, and let A be an accumulation point of the domain. So I've replaced all of that business about let I be an interval containing A, except possibly A itself. I've replaced all that with just let A be an accumulation point of the domain. So what I'm going to try and do here is define the limit for every accumulation point of the domain. So if f is such a function, then we'll say the limit as x approaches a of f of x is equal to L, if and only if. Okay, now this all looks very similar. For every epsilon greater than 0, there is a delta greater than 0, such that now here we have our first slight difference, such that if x is in the domain and the absolute value of x minus a is between 0 and delta, okay, then absolute value of f of x minus L is less than epsilon. So let's compare and contrast this to our old definition. I generally try not to put up things where I'm covered up with text, but I really wanted these two next to each other so we could really highlight what's going on here. So let's first sort of compare these two blocks. So sort of imagine this block here. So these blocks are going to be the blocks where we're setting up for what types of functions and what types of points are we even going to be able to talk about the limit. So if I compare these two blocks, right, this just says let A be an accumulation point of D. This is the one that says let F be defined on an open interval I containing A, except possibly at A itself. Okay. Anytime you have sort of two similar definitions, you sort of want to ask yourself, is one of these a generalization of the other? In other words, like, will one of these work for every case in which the other one works, but also work for some additional cases? Okay, so this new definition is going to generalize our old definition. If I have a function f which satisfies in a point A which satisfies these properties, so I have a function f, and I know that it is defined. And remember, we said we could sort of modify this to even say it's defined on some deleted neighborhood of A. Okay. If I have a function like this, then A is necessarily an accumulation point of D. Okay. So any function f which satisfies this property will also satisfy this. If f is defined on an open interval containing A except possibly at A itself, then that means that A must be an accumulation point of the domain. However, the converse is not true. It's not the case that if A is an accumulation point of your domain, that your function f will be defined on some open interval containing a, except possibly at a itself. So what we see is that this new definition generalizes. It takes all of the cases that this definition covers and expands them to an even larger set of cases. Now, that change, however, that generalization does require another small change down here. So let's come down here and notice if we sort of look at the if part of each of these. So you notice here that there's an additional condition. Here we say if x is in the domain and the absolute value of x minus a is less than delta, then absolute value of f of x minus L is less than epsilon. Over here, we simply say if the absolute value of x minus a is between 0 and delta. Now, what necessitates this change? Well, notice up here, the assumption was, again, that f is defined on an open interval I containing a except possibly at a itself. That means if you choose a delta small enough, then your function f of x must be defined for every, your function f must be defined at x for every x not equal to a, which this condition already ensures. So you always know you can find a delta small enough that f of x must be defined there. Over here, because we're only requiring that a is an accumulation point of the domain, it is possible that you could get arbitrarily close to a and still find points that are not in the domain of f. So here, you're basically saying you only need to check the points that are actually in the domain. I want not just the points that are close. I don't want all the x values that are close to a. I want all the x values that are close to a and are in the domain. Over here, we didn't need to make that distinction because once we got close enough to a, our hypothesis up here required that our function be defined. So there was no need to check. You could write if x is in the domain and this, but that wouldn't change the definition. So we throw that out. Over here, however, because you've relaxed the conditions uh, on a and on the function f, we need to add this additional condition down here to specify that we only want to check the x values that are actually in the domain. If x is not in the domain, f of x won't be defined down here, and it'll be impossible to satisfy this condition. Okay. So again, the old definition is exactly the same as the new definition if f is defined on an open interval I containing a except possibly at a. So these give you the same thing if f satisfies this condition. However, this condition is a weaker condition. Okay? A weaker condition means actually stronger definition. I need to assume less about my function, and I'm still able to produce the same results. Okay? This actually, while I'm erasing this, reminds me that, and this is nice because this is recorded, so it'll be in perpetuity. When I was defending my master's thesis, Dr. Sarah Rayner at Wake Forest asked me a question about whether only assuming weak convergence made the result stronger or not. And between the words weak and strong, I got so turned around I couldn't even possibly answer the question. She very graciously sort of asked me a couple of leading questions to work myself out of it. But so this is an example where a weaker hypothesis in the definition actually strengthens the definition. It makes it a stronger definition because we assume less. So hopefully with that, you'll never get tripped up by such a question. All right, so let's go back to this motivating example. So same function, okay? Now I want to see if I can find the limit as x goes to 0 of f of x. Now, if I go back to that picture, I feel like certainly if the limit as x goes to 0 of f of x exists, it must be 0, right? So I'm going to sort of guess that it's equal to 0. Now the question becomes then, can I prove that? Okay. So again, here my claim will be that the limit as x goes to 0 of f of x is equal to 0. I want to see if I can prove that using this new definition of the limit. All right. So these are the sort of standard epsilon delta type proofs. Okay, I want to show that for every epsilon, there exists a delta. So how do I do that? I'm going to choose an arbitrary delta, or sorry, not that. Choose an arbitrary epsilon. So let epsilon greater than 0 be given. And now what I'm going to show is that I can choose a delta, which may and will, in this case, depend on epsilon. But I can choose for any epsilon you give me, I can find a delta so that when x is in the domain and when the absolute value of x minus a is between 0 and delta, then absolute value of f of x minus L must be less than epsilon. Okay, so let epsilon greater than 0 be given. First, we want to note that 0 is an accumulation point of the domain D. That means we can actually talk about the limit, right? So now I need to figure out how I'm going to choose my delta. Now, for the time being, I'm going to leave a placeholder here. This is going to tell me for a given epsilon how I should choose my delta. I don't know yet, so I'm going to just leave a blank there. So choose delta equal to something so that when x is in the domain and the absolute value of x minus a, well, in this case, my a that's my a value, okay? So absolute value of x minus a is just absolute value of x. So that when this is between 0 and delta, we have, all right, now what do I want? I want f of x minus L. Oh, wait, my L is 0. So I want absolute value of f of x minus L. I want it to be less than epsilon, but I'm supposed to be proving this now, so I need to show that. I can't just write down, oh, that's true. And this is what I actually need to demonstrate. So the first thing I say is, okay, well, when x is in the domain, what can I say about absolute value of f of x? Well, when x is in the domain, f of x is equal to x, right? That's the whole importance, really, of this criteria, right? Is I need to know that when x is in the domain, that I can use this formula. So when x is in the domain, this will be equal to the absolute value of x. Now, what can I say here? Well, I know the absolute value of x is less than delta. But remember, I get to choose delta, right? And what I want is I want this expression here to be less than epsilon. So why don't I just choose delta to be equal to epsilon? So now notice that here what I have is that the absolute value of f of x is less than epsilon, which is what I want. Absolute value of f of x minus L is less than epsilon whenever these conditions are met, okay? So that concludes our proof, and hence the limit as x approaches 0 of f of x, in this case, is equal to 0. Okay. Now, this has been a rather straightforward first example of this expanded definition, but it is a case where, again, our previous definition would not work. Okay. But it's a fairly straightforward first example. In the next video, we will expand and look at many more examples. So the next video is going to be almost exclusively focused on looking at examples. And so we will look at more then. Okay. But at least for now, hopefully this has given you some idea of roughly the structure of these types of proofs. Now, the last thing I want to do is I do want to give one example of how we can also use this definition to prove things. Okay. So anytime you sort of define something, a natural question to ask is like, how many of them can there be? You do this lots. You have a polynomial equation and you wonder, how many solutions could it have? How many roots could it have? Um, if you define something, how many of these things even exist? Um, and so having defined a limit, we might ask ourselves, if I take the limit as x approaches a of some function, am I only going to get one number, or could there be multiple numbers that satisfy that? Well, sorry, before we get there, let me back up a second. Here's sort of a question I just want you to ponder. So think about the function, same function from before, same domain. And just looking ahead, I want you to ask yourself if this function is continuous at x is equal to 0. Or is f continuous on its domain? Remember, 0 is not in its domain, it's a separate point. So is f continuous at 0? And is f continuous on its domain? Now, let me sort of challenge you to be prepared to experience a little cognitive dissonance, okay? If we throw everything out and I just give you f of x is equal to x, that's the identity function, that's a polynomial. Everything about it just says to me it should be continuous, right? On the other hand, well, 0 is not in the domain, so can it be continuous at a point that's not in its domain? Normally, right, in the old definition of continuity, right, that would say no, right? It would say you can only be continuous at points that are in your domain. So that question under the old definition would clearly be no. The second part would also, I guess, be no, because even in our new definition of the limit, all the points of the domain are isolated points, not accumulation points. So we can't talk about the limit. And if I think my definition of continuity is the limit as x approaches a of f of x is equal to f of a, well, then that limit's not going to exist at any points in the domain. So certainly this can't be continuous. And if I look back at that picture from before, it looked like a whole bunch of dots. And like the very first, concept of continuity you probably had was something like, oh, it's something you can draw the graph without lifting your pencil. So I'm sort of stuck between these. I feel like f of x equals x should be a continuous function. And lots of other things are screaming at me, there's no way this can be continuous. Okay. What we're going to do is we're going to need to try to resolve that, right? So are we going to limit like what functions are continuous, right? And have like things like the identity function not be continuous, which in some ways could be a reasonable thing to do. Or are we going to expand our definition of continuity beyond just expanding our definition of limit, right? By expanding our definition of limit, we're already expanding our definition of continuity a bit, but maybe we need to expand our definition of continuity even a bit more. So that's something else we'll consider. Now, back to what I was referencing a minute ago. I actually want to show that if you have a limit, that limit is unique, which is to say you cannot have two values that are both the limit as x approaches a of f of x. Okay. Now, one of the reasons I like this is it gives a chance to prove a uniqueness result, which are, I study differential equations. Proving that solutions of differential equations are unique is an important part of studying differential equations. So I like uniqueness kinds of proofs. And it's a good chance to talk about how we prove these sorts of things. So how do I prove that something is unique? Well, the most common way is to say, well, what if there were two of them? Okay, so already by sort of posing a what if, right, we're sort of saying, okay, this is probably a proof by contradiction, right? So what if there were two, right? And then I'm going to show that, oh, well, if there are two, they actually have to be the same thing. So you can't actually have two different ones. Okay. So let's outline this proof here. Well, I say outline, we're gonna write out the proof. So assume towards contradiction that the limit as x approaches a of f of x is equal to some number L1 and the limit as x approaches a of f of x is equal to some other number L2, where L1 and L2, I'm assuming, are not equal. Okay. Now, let's sort of take piece by piece, okay, and ask ourselves, what would this mean? Okay. Well, this would mean that for every epsilon greater than 0, there exists a delta greater than 0, such that whenever x is in the domain and f of x, and absolute value of x minus a is between 0 and delta, then f of x minus L1 in absolute values should be less than epsilon. Okay, so how am I going to make use of that, right? That's just regurgitating the definition. Well, I'm going to need some sort of epsilon, right? So let me start by taking an epsilon. So I'm just going to take an arbitrary epsilon. Then looking at this, there has to exist some delta. Now I'm going to call this delta, I'm going to give a special name. I'm going to call it delta 1. So delta 1 goes with L1. There's going to be a delta 2 that goes with L2. So there exists a delta 1 greater than 0 such that whenever x is in the domain and let's see, what else do I want here? X in the domain and 0 less than absolute value of x minus a is less than delta 1, we have. Now, I can make this as small as I would like. I can make this difference as small as I would like. I'm not going to make it less than epsilon over here. I'm actually going to make it less than epsilon over 2. Right, so for an arbitrary epsilon, I can make this as small as I want. I'm going to make it less than epsilon over 2. Now, similarly, if I look at this piece, okay, I can write out a very similar statement. Okay, so there exists a delta 2 greater than 0, such that whenever x is in D, and absolute value of x minus a is between 0 and delta 2, f of x minus L2 is less than epsilon over 2. Now, at this point, there are some reasonable questions you may be asking. The first is, well, why are you even doing this thing with epsilon over 2, right? We'll see in a second why that's going to help us. And the other thing you might be sort of wondering is, well, why are we even using epsilon at all, right? We could certainly throw away this epsilon and just say there exists delta 1 greater than 0 such that whenever this holds, we have this is less than a half or 10 or 1 over a million. Like we could replace this arbitrary epsilon with a specific epsilon if we wanted to. So why are we keeping an arbitrary epsilon? And why do we take an arbitrary epsilon and then have these? Well, let's see. Remember, our motivation isn't to prove anything about these particular limits. We're actually doing a proof by contradiction, and what we're going to contradict is the fact that L1 is not equal to L2. That's the contradiction we're going to reach. Okay. So now what I want to do then is let me consider the difference between L1 and L2. And I'm going to put some absolute values on here. Okay. Now, the first thing I'm going to do is well, actually, there's sort of two great tricks of analysis in this proof. The first is that sometimes it's easier to rewrite something in a slightly more complicated form by adding and subtracting the same thing. So let me do that. So notice that what I've done here is in between L1 and L2, I've added and subtracted f of x, right? So I haven't changed the value of this, I've just re-expressed it. Okay. Well, now what I'm going to do is I'm going to apply the triangle inequality. And now I can swap this because it's really just negating that. And inside the absolute values, it doesn't matter. So then this will be equal to now, I'm actually playing a little fast and loose with this right now because I haven't really said what x is, right? I mean, I guess x must be some value in the domain, but I haven't said which one. And like, I mean, for this to even make sense, x needs to be in the domain. So, like, what is x? Well, we're going to actually get to that in just a second because, right, what my goal is going to be is I want to show that this difference is actually zero, right? If I show this is equal to zero, that means L1 is equal to L2, which is a contradiction, okay? So how would I go about this? Well, instead of showing something, this is the other great analysis trick. Instead of showing something is strictly equal to zero, show that it's less than epsilon for every epsilon greater than zero. There's only one non-negative number. This quantity has to be non-negative. There's only one non-negative number that's less than every other positive number. That's zero. Okay. So what I'm actually going to do is I'm going to show that this quantity has to be less than epsilon. Epsilon was taken to be some arbitrary thing, so it must be true for every epsilon. Therefore, this must have actually been zero to begin with. Okay. So what do I know? I know that I can make this quantity this quantity less than epsilon over 2 if I take an x in my domain with x between 0 and delta 1. Okay. So under some appropriate conditions, I can make this less than epsilon over 2. And similarly, I can make this quantity less than epsilon over 2 if I take an x in my domain satisfying this. Okay. So what I want to say is this is true, and that is just epsilon, right? For any x in the domain with, now what do I need? I need 0 to be less than x minus a. Now I need x minus a, I need it to be less than delta 1, and I need it to be less than delta 2. How do I make that happen? I make this less than the minimum of delta 1 and delta 2. So this is going to be true for some x values. I don't know which ones, but whichever ones, I'm going to take the x value in the domain that satisfies this. There must be some x value in the domain that satisfies this, precisely because A is an accumulation point of the domain in order for this to exist. Okay. All right. So what do we have? So absolute value of L1 minus L2 is less than epsilon for every epsilon, right? Because this was just arbitrary. So this absolute value must be equal to 0, and L1 must be equal to L2, a contradiction. So Having reached this contradiction, our initial assumption here must be false, and so hence limits must be unique. Maybe finishing the video. Oh, it's ran off the screen a little bit. That was a little two exclamation marks with a smiley face underneath. Okay. So what this proves, right, is that if we have a limit and it exists, there's only one real number it can possibly be. Okay. Now, we've now seen one example of the limit of a function that we can now take that we couldn't take before. We've seen one proof, right? We proved a theorem about limits of functions using the definition. And what we want to do next time is we want to look at some more examples. And the reason we want to look at more examples is having expanded our definition, right? We can imagine there may be a great many functions now for which we can discuss limits. And it's always helpful in analysis to sort of have a catalog of functions in the back of your mind that you can be thinking about when you're trying to test some theorem. And often you don't want the simplest cases, right? If your only concept of, if your only idea of a function is x squared, you're going to start to believe all sorts of things that are true for general functions that aren't. So, for example, if all the sort of models of functions that you have in the back of your mind are, x squared, x cubed, say just like monomials, then you're very quickly going to start to believe like that every function is continuous. You're going to start to believe that every function is differentiable, right? So you need things like absolute value of x or, sort of discontinuous types of functions, jump discontinuities. You need all of those things to help you understand what the most general theorems should be. So next time we are going to work with more examples to start building up that catalog of functions. Having done that, we'll then set about expanding our definition of continuity and then beginning to explore some of those consequences of continuity, things like the intermediate value theorem, things like the extreme value theorem, other consequences of continuity moving forward.